All right, functional set number 3. We're going to talk about the Minnesota functionals. This come out of a group at the University of Minnesota run by a man named Don Trular. He's been around, he's done a lot of work on chemical dynamics and is concerned with potential energy functions because in order to do dynamics, as those of you taking Chem 193 will find, you need a potential energy surface. So it naturally led him to density functional theory, which is much faster and can be quite accurate than compared to wave function theory. So here's the philosophy, and this may be the most controversial of the functionals that we're going to talk about. So let me take a step back for a second. It's probably now the functional of choice for most main group organic chemistry. So if you're going to do reactions like a Diels-Alder reaction or a Claisen reaction or a Cope reaction, then in fact, most organic chemists will turn this on in Gaussian. So it gets a lot of use. In addition, it's probably the most used set of functionals for transition metals. So organometallic chemists and inorganic chemists will turn it on. So all of that bodes well for it, and you know, success is its own reward. On the other hand, it is in the theoretical community looked on with some level of suspicion. And you know, that's good-natured scientific suspicion in the sense that they basically throw the kitchen sink at the functional. They put in lots of terms. They fit to lots of data. And it's not clear what limits it satisfies and what it doesn't. Okay, so you know that's a theory versus experiment sort of thing. But they claim, at least for the M06 and M06 2X functionals, it reduces the uniform electron gas in the low gradient limit. That's what we want it to do. They fit to lots of different kinds of data. Maybe not as copious as you'd like, but you're going to see they're worried about lots of different properties. They're more than happy with various functionals for various purposes. So there's going to be a functional M06 that's good for transition metals. For main group, there's going to be an M06 2X. For solids, there's going to be an M06 local. But these people are also happy with hybrids. You know, PBE wasn't. B3-LIP was happy with hybrids, and that's just what they do. So here are the functionals. And these are the most common ones right now. There's M06, M06 2X, M06L. All of them use the gradient, the kinetic energy density, which is like a second derivative of density. So this is a meta GGA. They are hybrids. And this one's best for transition metal containing species. And they know that based on a series of tests. M06 2X, not increased, but increased exact exchange. It's best for main group, and it's current standard in organic chemistry. It does a good job, particularly on barriers. M06L removes the hybrid nature of the function. It's good for solids. And I really don't have a way of assessing how it compares to PBE, but there are lots of people who use it for solids. So here's the article, and now, you know, the equations are dense because of the functional forms that they use for the exchanging correlation functions. But you could read this now, and you see what it's doing. Main group thermochemistry, thermochemical kinetics, so that means barriers, non-covalent interactions, excited states, and transition elements. So that's what they're aiming for. And apparently this was the first one to get a decent job on non-covalent interactions of about 3 angstroms. Their targets then were transition metals, transition states, non-covalent interactions, spectroscopy, and main group thermochemistry. That's what they want. The forms are akin to what we've seen before. They are determined by training sets. And the bottom line is the results are generally better than B3-LIP, PBE, PBE0, and non-training set tests. Certainly for barriers, it's a real improvement. In general, although in calculations we've done with Professor Dowd Turns out B3 does pretty well for relative barriers. So the key is here, this seems to be an improvement based on the utility it has shown for organic chemists. So that's good. There's a piece, again, of the theorist that worries, well, I don't know why it gets it all right. But in the end, you know, if it's vast calculation, it gets the right results. As a student said to me, when I talked about this with her, I said, you know, it just feels creepy that you just fit the heck out of it and you don't know what's in there. And she says, why does that bother you if it gives you the right answer? So I think that's a tension each of us has to decide about and live with. So I'll stop there.